All right, so I want to run through some of these paper one problems just to get you refamiliarized with the material that we covered last year. So problem number one, we want to know which unit is equivalent to joules, kilograms to the -1. And let's just kind of review here. Joules is the unit of energy and also the unit of work. And let's just review a couple of things to get some consistencies here, something you might not have thought about. For example, kinetic energy has a formula 1/2 mv squared, right? And let's just examine those units closely. So that's going to be kilograms times and meters per second, meters per second, that's velocity. And then we go ahead and square that. What that means is that we're going to get that this is kilograms meters squared seconds to the -2, right? So that's one way of saying it. Now let's look at another completely different form of energy just to kind of show the idea that regardless of the energy form you choose, the units are always the same. The units are going to be kilograms. Gravity is acceleration, so that's meters per second to the -2. And height is, again, here in meters. So when we smash all these units together, once again we get kilograms meters squared seconds to the -2nd power for our unit. This is how every form of energy works. Not only that, this year we talked about how work and energy have the same unit. So let's look at the unit of work. Work is force times distance, which is going to be newtons, right, times meters. Now, what does that have to do with this unit of energy here? Let's be clear. Well, what is a newton? Force is mass times acceleration. So that's kilograms meters squared seconds to the -2. So this whole unit here is what we call a newton, the unit of force. So when I say it's newtons times meters, that's really going to be kilograms meters squared seconds to the -2. Sorry, that's meters per second squared, not meters squared for the newton. Kilograms meters to the seconds times seconds to the -2 times this extra meter here. So that's going to give me kilograms meters squared seconds to the -2. So this thing that I'm calling a joule in every case can be broken down into fundamental units as kilograms meters squared times seconds to the -2. So if we want to know which unit is equivalent to joules, kilograms, what we need to do is we need to multiply out a little bit. So this is going to be kilograms meters squared seconds to the -2 times kilogram to the -1. These two will cancel, and that's how we get choice D as our answer for number 1. Moving on to problem 2. So here's what we're saying. The component of velocity in the xy direction is 4 meters per second. But let's be clear, this is not the whole axis. What we're saying is that we have a component here that is 4 meters per second. And we want to know the component in the xz direction. Well, what that means is in the xz direction, in order to make this a 3, 4, 5 triangle, I'm going to actually pick up this piece and put it over here, and then we clearly see that this component here has to be a 3-unit long component. And that's how I'm getting B for my answer. Now, what is the definition of a mole? This is something we're going to be getting to a little bit more clearly next semester, but since you've had chemistry sophomore year, let's just clarify a couple things. So, a mole is the amount of substance. Let's see, so the amount of substance has the same mass as 1 atom of carbon-12. No, that's not going to work. We know a mole is 6.02 times 10 to the -23rd particles, but what does that mean? The amount of substance that contains as many electrons as the number of atoms, 12 grams of carbon-12. No, it's not a mass. The amount of substance that has as many nuclei. No, it's the amount of substance that contains the same number of elementary entities as the number of atoms in carbon, 12 grams of it. Because here's the thing, I could actually have a mole of moles, for example. I could have a mole of erasers. I could have a mole of eggs. So this one doesn't work because one carbon-12 atom has a really small mass. Here, no, 6.02 times 10 to the 23rd atoms of carbon-12 has a certain fixed mass. That's not a mole. That's just going to be fixing mass. And then here, the amount of substance that contains as many nuclei as the number of nuclei. No, that's not necessarily true because we don't need to measure moles in just nuclei. So that leaves us choice D as our answer for number 3. Then number 4, let's express watts in terms of fundamental units. Watts is power. That's going to be joules per second. When we say fundamental units, let's review our fundamental units. So fundamental units are meters for length, seconds for time, moles for amount, kilograms for mass, candela for luminous intensity, right? The candela. We have amperes for current, and we have Kelvin for temperature. Okay, so 1, 2, 3, 4, 5, 6, 7 fundamental units. So watts, joules per second, which is going to be, again, Newton meters per second, because joules are force times distance, Newton times meters. That's going to be kilograms, mass times acceleration, kilograms, meters squared, seconds to the -2, okay, times meters, times, here, seconds to the -1. So when we simplify all that out, it's going to be kilograms, meters, Problem number 4. So we want to express the watt, the unit of power, in fundamental units. And watts are joules per second, which is going to be newtons times meters divided by time, which is newtons meters seconds to the -1. That's the seconds on the bottom. So that's going to be kilograms. That's mass times acceleration. So kilograms, just kilograms, meters per second squared, times meters times second to the -1. So when we smash all these units together and simplify, we're going to get kilograms, meters squared, seconds to the -3, which is choice D. By the way, when we say fundamental units, let's just review the fundamental units quickly. So we have length, measured in meters, mass, measured in kilograms, temperature, measured in Kelvin, electric current, measured in amps or amperes. We have luminous intensity, measured in candelas. We have amount measured in moles, right? So number of particles measured in moles. And we have time measured in seconds. So those are our fundamental units, and whenever we say fundamental units, it needs to be one of these 7. Since we're talking about mechanical quantities, we're going to be restricted to length, mass, and time. Problem number 5. The graph shows an experimental result to determine the density of oil. We have systematic errors and random errors. So what can we say about the measurement used to find the density of oil? Well, we would expect that as far as it goes. We would expect our line to kind of nicely connect at 0, 0, but we seem to have rather a large systematic error. But if you look at our random errors, it should be a nice linear plot, so we seem to have small random errors. So I'm getting choice C as far as our answer goes, because what we'd expect is this line to really be centered around the origin. So I'll show you what I mean. If I were to just kind of take this line and draw it, I'm going to hope this works. This line should be kind of nice and linear through here. Okay, it's right through those points. We would expect it to actually run through the origin because as your mass goes to 0, your volume should go to 0. But instead, we get this strange line that is clearly off the mark. So we get a nice consistent slope, which we expect for a nice constant density. So we have a large systematic error, but very small random errors. Which of the following is the fundamental unit? It is an ampere. Please memorize those. All right. Now, the radius of a sphere is measured with an uncertainty of 2%. What is the uncertainty in the volume? So volume is pi r cubed. So we just add up those percentages to get 6% error. Just to be clear, that's going to be 2% plus 2% plus 2% because we have 3 r's multiplied together. And that's how I'm getting 6% error. Now here, a force acts on a car moving at a speed v given by F equals kv squared, where k is a constant. What is the unit of k? So let's be clear. F is measured in newtons. K is what we want to know. And v is measured in meters per second. And we're squaring that v in this formula. So newtons is kilograms, m, times a, meters, seconds to the negative 2. And that's going to be this k here times meters times seconds to the negative 2. And now we can actually cancel units on each side. So we have this canceling. And this is meters squared, sorry. Only one of these cancels. And so what we actually end up getting is, we end up getting that the units here are kilograms per meter on our, or rather to write it in IB notation, kilograms times meter to the negative 1, which is exactly choice A. Now for problem 10, which of the following has the units of energy? We've already talked about this. Work is force times distance. We can use any of the calculations from before. Work and energy have the same unit, so newtons is kilograms, meters, seconds to the negative 2 times meters for the x part. And that's going to give us kilograms, meters squared, seconds to the negative 2, which is exactly choice B. All right, in the next set of videos, we will actually look at the kinematics problems and contrast those with what we've been doing for measurement.